everyone. So thank you for the introduction. So our main motivation behind this work is to enable safe interoperability between languages of different kinds. And this is important because software systems are rarely implemented in a single language. And so in an ideal world, we would like languages to be able to interoperate in a flexible and safe way, meaning that data structures can be shared and not copied across language boundaries, and that abstractions and safety guarantees of its language are preserved. And how can we make all of these languages interoperate? We can compile them to a common target. And with more than 40 different languages compiling to it, WebAssembly is an excellent candidate to enable safe language interoperability. However, WebAssembly currently lacks any support for safe interoperability, and some of these languages have different memory layouts and even different memory management styles. For example, Amal is garbage collected, while Rust has unique memory ownership that allows the compiler to safely free memory without the need of a garbage collector. So we want to study this problem, and in order to study it, we pick two representative source languages. We pick CoreML, which is a type-safe, high-level language with garbage collected heap, and we pick L3, which is a language with unique memory ownership, enabled with linear types that guarantee that references have a unique owner at any point during execution. What can go wrong when such languages interoperate? Well, let's look at an example. So here's an L3 program, and it's using some functions from a CoreML program. So it uses the inc function that increases the contents of an integer reference by 1, and it's calling the inc function on a new linear reference. So this inc function, however, stashes the reference that it's being passed to it as an argument into a closure. After the return of the function, the L3 type checker thinks that the ownership of this reference is unique, so it thinks it's safe to deallocate it. And later on, the L3 program calls the read function that tries to dereference the stashed location, which has just been freed, which is a use after free error that will cause the program to crash. So we would like to use WebAssembly to enable safe interoperability between these two languages. And we would like to do it by sharing memory in a fine-grained way while maintaining strong safety guarantees. But currently in WebAssembly, memory sharing has an all-or-nothing flavor, and current interoperability proposals focus on share-nothing interoperability. So let's look at the Wasm memory model and see why we cannot share memory in a fine-grained way. So typically, modules in WebAssembly can refer to a single memory. This can be their own private memory, as in this case, or a module can import another module's memory and treat it as its own. However, this leaves the entire memory of module A exposed to module B that can do pointer arithmetic to access private data. So the multiple memories proposal attempts to solve this by allowing multiple memories to coexist, and modules can refer to multiple memories. So this way, a module can have its own private memory and a public memory that is imported to another module. This allows memory sharing, but it's still in a very coarse-grained way. And in addition, there is no support for sharing memory between different memory management strategies, and also abstractions, for example, linearity, or in other words, unique memory ownership in this case, and safety guarantees may be violated. So in this work, we develop RichWasm, and we intend this to be a platform for safe interoperability. RichWasm is a typed intermediate representation built on top of WebAssembly, and it has rich types and capability types in order to capture memory ownership. In our work, we provide type-preserving compilers from CoreML and L3, and source programs can communicate with a simple FFI. Then type-checking the RichWasm code at link time will raise a type error when memory safety is violated. After type-checking, we can lower the RichWasm code to WebAssembly that essentially erases types, and we can run it in a number of different environments. Let's dive deeper into RichWasm, and let's start from its memory model. So RichWasm has two global memories that are shared across all modules. There is a garbage collected memory, and the references to it can be freely copied. We call this the unrestricted memory. And there is a manually managed memory, and references to it have to have a unique owner at any point during a program's execution. We call this the linear memory. And unlike memories in WebAssembly that are byte arrays, these memories are high level and they are maps from locations to values, and only pointers to the beginning of data structures can exist. So we cannot do pointer arithmetic. The memory contains structured data that can have one of these types. They can be variants, they can be structs, arrays, or existential type packages. And a central feature of the type system is pointer types and capability types. So in order to access a memory location, we do it through both a pointer and a capability. And the capability essentially captures the ownership of a memory location. And the capability type is annotated with the privilege it grants to the location that can be read or read-write, the location itself, and the type of the contents of this memory cell. So, and while capabilities to unrestricted memory can be freely copied, capabilities to the linear memory cannot be freely copied. We need to have a unique owner at any point during the program's execution. So how do we ensure that? We add qualifiers to types that denote in which way a value should be treated. So an unrestricted qualifier denotes that the value can be freely copied, while a linear qualifier denotes that a value is linear. Therefore, we cannot, and typically, pointers to locations, even regardless of whether they are pointers to the unrestricted or linear memory, they are unrestricted because they do not capture the ownership, while capabilities to linear locations have to be linear to ensure the invariant, the unique memory invariant. So WebAssembly, RichWasm has a reference type that conveniently packs together a pointer and the capability to it, and we can split a linear reference into a linear capability and an unrestricted pointer. And this restriction between pointers and capabilities allows us to have multiple pointers pointing to the same linear location while ensuring that the ownership will be unique. Therefore, multiple parts of the program can hold a linear pointer, while only part of a program can have a linear capability. So in our formalization of the language, we axiomatize garbage collection, and we assume that both the unrestricted memory and the linear memory can point to each other. There is a complication that arises from garbage collecting these two memories, and the thing is that the garbage collector may end up owning linear memory. So imagine the scenario where we deallocate some piece of unrestricted memory, and this memory points to linear memory. And now the garbage collector has to do something with this linear memory, which is to deallocate it. So the garbage collector needs to be able to free linear memory when collecting unrestricted memory. Let's look at how the RichWasm type system works in practice. And here's a module A. It has an unrestricted reference to a location that has an array, and it can freely pass this to another module while keeping a copy of this reference, and the garbage collector will ensure that when there are no more references to this location will be deallocated. And then if this reference was linear, the module A can still share this reference to module B, but it cannot keep a copy of this reference, and the unique owner of this reference can always call free on it, and it will be a safe operation. This is a function example in RichWasm. This is the type, and what this function is doing is that it takes as input a linear reference to a struct with a single struct field, and it outputs the contents of this field. This is the type of the function, and let's unpack it. So this is the input type. It's a linear reference that points to a struct, and the struct has a single linear field that has type alpha, which has a linear qualifier. Alpha, the function is polymorphic on the alpha type, and it's also polymorphic on the location of this reference, so that we can instantiate this with any concrete location at runtime. And the output is simply the contents of the only struct of the only field of the struct. So notice that this function does not return back the reference, so it must consume it. And it must do that using free, otherwise this program will not type check. So during execution, the function will put its argument in a memory slot where arguments and local variables are being stored here. And this is a reference to L1, and L1 is a pointer to a reference to the linear memory, and it has a struct with a single field. So we cannot just simply read out the struct field, because that would violate linearity. We would suddenly have two copies of this 42 here, and we know that 42 is linear. So we cannot simply do that. We have to use a struct swap instruction. And this lets us read the contents of the struct field, and as soon as we read it, we put in the struct field a new value. And here we decide to put 43. So struct swap will take two arguments from the top of the execution stack, ref L1 and 43. Okay, but now we have a similar problem here again. We have two copies of a linear reference, and we should never do that. It violates our invariance. So what can we do? We want to swap the value of the local slot, but it's not obvious this time what should we put in, because we cannot create a linear reference out of thin air. So it happens that we need to change the type of the slot, and we put unit inside. And this is all good because we now have, again, just one copy of the linear reference. And this demonstrates the need for strong updates. A strong update is when the type of a memory slot changes dynamically during execution. And we need that to ensure linearity, and we need to be able to do strong updates on struct fields and local variable slots. But in order to ensure that a strong update is safe, we need to keep track of sizes statically. So we statically check whether a new type we are trying to put in a memory slot fits in the available space. So we have several type annotation types in order to track this information. And this is the full example showing the hidden size information. And we can see that the struct field is annotated with its size, here 64 bits, and that the alpha type has an upper bound of 64 bits. Okay, there are more types in RichWasm that I didn't mention in this talk. We support all WebAssembly types and even more types, including recursive types, existential types, and polymorphism over types, location, qualifiers, and sizes. This is the shape of the RichWasm typing. It closely mirrors the WebAssembly typing, and it gives a type to an instruction list. An instruction list has an arrow type that denotes like the argument, the top of the execution stack before the instruction list is being executed, and then the top of the execution stack after the execution of the instruction list. So in our case, typing is more complicated because we have to keep track of more information. We have typing environments that, again, look like the typing environments of WebAssembly. We have the store typing that keeps track of the typing of the unrestricted and the linear memory. We have the module environment that keeps track of the function types and the types of global variables. And we have the function environment that, as in Wasm, it keeps track of the return types and also the return types of the dump location. But also in our case, we use it to keep track of our polymorphic variables and their constraints. And we have a local environment that keeps track of the types and the sizes of local variable slots. So the thing here is that because we can do strong updates on the local environment, it has to be threaded so that these strong updates, the changes of the types, can be communicated with subsequent parts of the program that is being typed. And we have formalized RichWasm in Coq. We have proved progress and preservation. Our statements look similar to progress and preservation of WebAssembly. And now let's go back to the original example and see how RichWasm would have prevented the error. So we consider designing sophisticated FFI's future work. So here what we do is we simply tweak core ML to add some linear annotation, which is denoted in red angle brackets. And this is linear references that come from the L3 world. So here we can try to compile this to RichWasm, but the RichWasm type checker will complain because we do not treat a linear reference linearly. So in order to fix that, we have to remove the stasing of this location. And this is an example that goes through the RichWasm type checker and can be compiled all the way to WebAssembly. So to summarize, we presented RichWasm, a typed intermediate representation that has rich types and capability types that ensure unique memory ownership. And we provide type-preserving compilers from Core ML and L3, and also a compiler that lowers RichWasm to WebAssembly by essentially erasing types. And we have a Coq formalization and type safety proof. So there's a number of future directions that we would like to investigate. First, we would really like to be able to compile to Wasm plus the native garbage collector for WebAssembly that is being implemented. But we currently cannot because we need support for finalizers to deallocate any linear memory pointing to by unrestricted memory that is being deallocated. We would also really like to compile Rust to RichWasm. And in order to do that, we would need support for compiling immutable borrows to RichWasm. And then we would also like to build sophisticated FFIs between real-world languages that all compile to RichWasm. Then we would also like to investigate interop between other languages like C, but these languages do not have enough type information to be compiled to RichWasm. So we would want to do safe interop between WebAssembly and RichWasm. And we conjecture that that could be an instance of gradual typing. So that was all for today. Thank you very much.
Okay, we have time for questions. In the meantime, if the last speaker is here, please approach the front.
Hi, thanks for the nice talk. So I'm just thinking about the resolution to you had the opening example with the stashing the reference, and then the resolution was, oh, actually, our ML-like language now needs to be extended with linearity in order to do
yes.
this, right?
So I forgot to mention that, but ML is agnostic to this linear annotation, so it's simply a directive to the compiler to compile everything annotated with that to a linear RichWasm reference. But the type checker is still agnostic to this linearity annotation.
But I guess the programming model that emerges is basically that the ML-style programmer still has to understand linearity, otherwise their stuff won't link, right?
Yes, if you want to communicate with a language.
I think there are other ways you could approach that, but that's,
yes.
maybe we'll chat about that later. Yeah.
Okay.
Thanks.
Mm-hmm.
I maintain a couple of large OCaml libraries with a lot of interop with like C and Rust and languages like that, and not just like, you know, GC versus like linear semantics are a problem, but just like getting them to agree on the types in the first place is kind of annoying, and I don't really care about Wasm. Like, have you thought at all about like how this could apply to just like the general problem of getting languages to interop nicely?
Yes, it's a platform that we can build like safe FFIs on top of that. Like eventually the end user, the programmer, wouldn't need to know anything about RichWasm, and like given that we have good errors at the RichWasm level that like give you enough information about the source level programs, but as an end user of this, you would only have to know the FFI between the source languages.
Okay, let's thank our speaker again.